Okay, so let me just recap where we got to when we talked about lists previously. Now I'm actually putting some types in my Haskell script so you can connect the definitions and the types. So here's a list of int. And what is an int? Well, it's like an integer, but it's a kind of computer integer. That is to say, it's an integer, but it has a kind of fixed size. It means it takes up a fixed amount of space in a computer. So in most programming languages, when you have something like an integer, they're not really integers in the mathematical sense. They're sort of bounded integers. And that's what int is. So when you need integers, but they're never going to need to be really big, then int is a reasonable choice to use. I think the biggest size you can represent with an int is something like 2 to the 63. Or maybe it's 2 to the 63 minus 1. So if you go beyond 2 to the 63, weird things will happen. Maybe I can. So if I type 2 to the power of 63, there'll be nothing wrong with that because it will assume I've got integers. If I want this to be an int, I can actually force it to be an int. Let me by saying, give me that, but actually what I mean is as an int, not an integer. And you notice you get a slightly strange result. I don't know if you can see that. There's a minus sign there. So that's a pretty wild error. So if you use int and your numbers get really big, weird things will happen. Anyway, not to worry. This is about lotto numbers. These are my winning lotto numbers. So int is fine. So this might be the list of winning lotto cards for a given week. It's a list of lists. You notice the way we write the type of a list of lists. This is a list of int. This is a list of lists of int. That's a list. I've defined it over here. That's an int, and so on. We've also seen a built-in function or operator, this sneaky notation here, which is kind of a bit special as a notation in Haskell. Because you can't define this from scratch. It has to be sort of built into Haskell. But this allows you to give simple enumerations of values. It works for numbers, but it works for anything which is sort of bounded and can be listed in order. For example, characters can be listed in this way. And we could have defined factorial from integer to integer by generating all the numbers from 1 to n and then taking the product. And of course, when I say generating all the numbers from 1 to n, maybe sounds like that's the way that Haskell would actually work this out. It won't actually necessarily do things in that order, but it will get the same result as if it did things in that order. Haskell uses sometimes a more cunning order. Sort of when it has to build something big, it'll just build a little bit of it. Say, I'll just start with a little bit of it, because sometimes that works out more efficient. Any questions? So this is just a recap of what we did with lists so far. And there are lots of standard functions, and you can probably guess what most of these are. They apply to a list of things, reversing a list, how long is the list, adding all the things in a list, multiplying, taking the biggest thing in a list of things which can be compared, so on. This one, very useful, is an operator for combining lists by joining them together. So you give it two lists and it gives you one bigger list. So they're all standard functions and there are loads more. We'll learn about those as we go along. We'll see how to define many of those a bit later. And what we saw is that strings are just another kind of list, just with a special way of writing them down, so they look nice. We saw that in the Kahoot. So what I want to cover that's new is list comprehensions. So I'm going to start with an example of the table of the powers of 2. So you give it a number n, and the definition is here, but I'm going to talk about that in a second. So let me hide it just so you don't get too distracted, get too excited. We're computing the powers of 2 from 0 up to n. So that's what power table is. So for example, power table 7 will give 2 to the power 0 2 to the power 1, 2 to the power 2, and so on, up to 2 to the power 7. Okay? So here's a definition. And this is a definition by using a list comprehension. So let me explain this definition in bits. So we're going to build the definition. The core of the definition is going to be this list. This is like the engine that's going to be, we're going to use to build our table. The numbers from 0 up to n. So we know what that is. So what this expression says, I'll read it to you the way that I would read it in my head. This says, this is the list of values 2 to the power x, where x is drawn from the list 0 up to n. So the list of 2 to the x, where x is taken from the list 0 up to n. So what this does is it gives a value for x for each of these things in the list, and then we build a list of those 2 to the power x's. So this vertical bar separates the things that we're building from the things that we're going to use to build it. And this is usually called the generator. And this symbol here just means we're going to take x from this generator. So x is not mentioned anywhere. So this x here is like the parameter. There's no x is not defined somewhere else in the program. This is where x comes from. So we're giving a name to the numbers that we're taking from 0 to n, calling it x. And for each of those, we're going to produce 2 times x. So here's another example. 10 plus y for every y taken from the list from 1 to 5. So what do you think about a little bit what you expect that to produce? Well, for every number in the range 1 to 5, it's going to add 10 to that number and produce a list of the answers. So it gives you 11, 12, 13, 14, 15. Okay, here's another example. So if we wanted to work out the sum of the first n squares, so you take the numbers from 1 to n and you square them all. So you get 1 squared, 2 squared, and 3 squared. So you get a list of all the squares. If we copy that and paste it down here, in order to run it, we need to give a value for n. So let's give 5. So you get all the squares, 1, 4, 9, 16, 25. And if we use the built-in standard function sum, we can add those all together. So that would be the sum of the squares up to n. You'll see these kind of series, I'm sure, in your discrete maths course. So here's another example. We can also use multiple generators. So you can have, instead of just one generator to create your list, you can have more than one. So let me run this and see what we get. Example 2 generators. Okay, so this is the example of 2 generators. So what do you notice about the result? Well, we get all combinations of y and all combinations of y's and x's. So we have a total of 5 different values, but we get 6 different results because we get 2 times 3 possible combinations of y's and x's. And you see that the order of these 2 generators matters. This one sort of changes. For 100, you choose 100 here, then you'll go through 1, 2, and 3 here. Then you'll choose 200 and go through 1, 2, and 3. So if you swap the order of the results will be different in this example. Okay? So these are very powerful ways of building lists. You can do a lot of things with these list comprehensions together with these predefined functions. Okay, so let me introduce another feature. And I'll take the example of the powers, 1 squared, 2 squared, 3 squared. So the powers of, 2 to the 0, 2 to the 1, 2 to the 2. The powers of 2. But we want a function which returns all the powers of 2 which are no larger than some number n. So say, I want all the powers of 2 which are no bigger than 10,000. So I want the powers up to some value n. And what I'm going to do, I'm going to build a list comprehension to get those. And I'm going to use, as a generator, my power table. And let me take the power table, well, let's take it up to the value n. Because will this work? Not quite, roughly. I don't need to go higher than n, but I suppose in the case of 0, I might need to go to 1. No, that's fine. I think it works. So I take all the powers of 2 up to n, but I only want the powers of 2 whose value is no bigger than n. So I'm going to take all the powers from that list, but that will give me too many. So what I can do is add a guard to this expression. I can filter out the ones that I want by adding a Boolean expression. I can say, yes, I want all the values of p from the table, but I only want the values of p if p is less than or equal to n. So don't give me any powers of 2 which are bigger than n. So this thing here is a Boolean expression, and it kind of adds a filter. It sort of lets us only keep some of the values that are generated by this generator. Maybe not the absolute simplest example, but let's have a go. Powers up to 10,000. So what are the powers of 2 up to 10,000? Well, the largest power of 2 before you hit the 10,000 limit is 8,192. The next power of 2 will be double that. So it will be too big